For the next few minutes, we will be discussing camshafts, valves, and their mating components. These parts are essential to diesel operation because without them, combustion could not occur. Camshafts and valves control the entry and escape of air and exhaust gases to and from an engine cylinders. On the intake stroke, the camshaft rotates to push the intake valve open, allowing air to pass through a port in the cylinder head into the combustion chamber. Then, on the exhaust stroke, another lobe on the camshaft pushes an exhaust valve open. The piston pushes the exhaust gases out through a port in the cylinder head into the exhaust manifold. This is the whole function of valves and cams, to provide a controlled method of letting air in and exhaust gases out. On the 3500 series and the 3600 series engines, the valve camshaft also serves as the fuel camshaft. Let's take a look first at camshafts. This slide shows the various parts of the camshaft: the cam lobe, the bearing journal, and the shaft. The valve is closed by the valve spring and opened by the cam lobe. The lobe pushes up the lifter and push rod, forcing the rocker arm up. The arm rocks against the valve and opens it. All of the Caterpillar diesel engines of today are of the in-block or pushrod design. The 3400 1.1 liter, 1.7 liter 3500 and 3600 series use this design in a 4-valve configuration. Here, the 2 intake and the 2 exhaust valves work simultaneously and are acted upon by the same pushrod from the camshaft. The rocker arm works against a bridge, which in turn pushes 2 valves at the same time. This rocker arm pushrod assembly is called bridge work. In one rotation of the camshaft in any 4-cycle engine, each valve will be opened only once. We are looking at one pair of valves, intake and exhaust, for one engine cylinder. From left to right, we see the relationship between camshaft rotation and valve movement. While the camshaft is making its first quarter turn, the intake stroke of the piston, the intake valve is fully opened. During the next quarter turn, the compression stroke, both valves are closed. Both valves remain closed during the next quarter turn, the power stroke, and the exhaust valve is opened during the final quarter turn, the exhaust stroke. Caterpillar camshafts are produced from forgings, castings, and bar stock. The determining factor in how a camshaft is manufactured is the amount of stress it is expected to withstand in normal operating conditions. Therefore, only our smaller 3200 and 3300 engines have cast camshafts, while 3400, 3500, and 3600 are forged. Recent innovations have allowed the 1.1 liter and 1.7 liter camshafts to be made from heat-treated bar stock with no interrupted cutting. As you can see, camshafts begin as rough forgings or castings. Once the rough camshafts are received, they are machined and heat-treated. First, the sides of the lobes and the thrust grooves are machined. Then the main bearing surfaces and lobes are rough-turned. The next step in the production of Caterpillar camshafts is the heat treat. This is a critical step, providing for strength and wear life. Some Caterpillar camshafts are hardened through furnace hardening and others through induction hardening. Then the camshafts are tempered to remove residual stresses. As tempering removes the stresses, it increases the toughness or the ability of the camshaft to withstand shock loads. The hardness after heat treatment is in the range of RC56 to RC60. This slide shows a cross-section of a journal and lobe and illustrates the hardened case depth after heat treat. This case depth or surface hardening is critical to a long wear life. Another straightening step follows heat treatment. After straightening, the journals and cam lobes are finish ground. This is a precise machine operation in which the cam lobes are ground to specifications of plus or minus thousandths of an inch. Camshafts are continually inspected during manufacturing to assure exact dimensional and metallurgical specifications are being met. To preserve camshafts, The last step is an oil spray. From there, they are either shipped to the assembly lines or shipped to the parts departments for part service. Because of the quality of Caterpillar camshafts, they can usually be reused at overhaul time. Northwest Motor Welding, Power Engineering, and Precision Engineering are a few of our competitors. Let's move on and discuss valves. As we said before, the valves control the entry of intake air and the escape of exhaust gases from an engine cylinders. Before we discuss the design and manufacture of valves, let's familiarize ourselves with the nomenclature. The uppermost end of the valve tip and the grooves near the tip are called the valve spring keeper or retainer grooves. The midsection is known as the stem, while the large circular area at the bottom is the head. The ground and polished area of the valve head is called the seating face. When the valve is closed, the face seals the combustion chamber by making contact with the valve seat in the cylinder head. The seat is also ground to a fine finish. On some engines, the valve seats are replaceable inserts. The 3200 series cylinder heads have no intake valve seat insert, but they can be adapted to accept them at overhaul. Thus, we need to manufacture a valve that will do a good job of sealing and venting our cylinders at various points in the combustion cycle. It must be able to withstand the heat and pressure which is generated during combustion without warping, cracking, or distorting. The stem is subject to wear from friction with the mating valve guide, while the face of the valve will wear against the valve seat. Wear resistance is also important at the tip, as it is peened millions of times by the rocker arms. In fact, on a 3208 at 2800 RPM, the valve tip is peened by the rocker arms about 84,000 times in 1 hour of operation. The face and the seat are ground at different angles. This produces a small 3/4 degree interference angle. It means that a thin line contact is made, which provides for high contact pressure between the face and the seat, providing a tight seal all around. Perhaps this is a small detail, but it is one that makes an important difference. Other parts of the valve mechanism are the valve guide, the retainer and spring, and the valve rotator. The valve guide is inserted into the cylinder head and does exactly what the name implies: guides the valve as it moves up and down to keep it steady. The valve spring pushes against the rotator to hold the valve closed and create the sealing action. A feature of Caterpillar engines is that most are equipped with valve rotators. This simple device turns the valves a few degrees each time the valve is opened. The rotator increases valve life. It evens the wear pattern on the valve and seating face, reduces buildup of deposits, and keeps a uniform temperature on the valve head. The design of the 3200 series engines permits their valves to rotate slightly without such a device. In addition, intake and exhaust valves from the same engine are not identical. In most cases, intake valves will be larger to aid the engine's breathing. The high cylinder pressures after combustion will readily vent the exhaust gases, even through a smaller port. Lastly, exhaust valves are subject to much higher temperatures and are often made from different materials for added heat and wear resistance. In order to match the material to the job, many valves are composites made from 2 or 3 different materials. The materials are different because the stresses and temperatures will vary relative to location. Valve stems are generally produced from moderate alloy medium carbon steel. The body of the stem is heat treated for wear life, while the keeper area is selectively heat treated so that it is through hardened. The stem is inertia welded to the valve head, which is made from special materials which give it greater fatigue strength, wear life, and higher temperature stability. In some cases, an expensive hard facing is applied for resistance to wear and guttering across the seal face. Guttering is when a channel burns into the face, preventing the valve from sealing completely. Inertia welding is a friction welding process pioneered by Caterpillar in which the two pieces are spun at very high speeds, then pressed together to form a strong weld. Caterpillar properly matches the metallurgy and construction of their valves to the specific job required. They vary from light-duty intake valves of one-piece construction to heavy-duty exhaust valves made of 2 or 3 different materials with hard facing. A good example is the 3306, which has 3 different exhaust valves due to low, medium, and high compression engine arrangements. This results in saved money for the customer because they don't have to pay for expensive heavy-duty exhaust valves if they buy a lower compression engine configuration. So Caterpillar feels it is necessary to job match the valve in order to give the performance and reusability our customers demand. Only Caterpillar is in a position to calculate the exact way in which to achieve a perfect match between the properties of the valve and a specific Caterpillar engine. The valve stem moves up and down in the valve guide, and a close fit is necessary to minimize gas and/or oil leakage. Valve guides are precision bored from graphitic gray iron. The flakes of graphite in this type of gray iron assist in self-lubrication of the contact surfaces. Most Caterpillar valve guides are threaded. This is a distinct advantage because the clearance between the valve and the valve guide can be kept to very small tolerances while allowing an oil path for lubrication. An exception is the 3200 series engines, which have no valve guides. With these engines, the stem bore is knurled to allow a path for the oil. Valve springs are used to pull the valve shut over the inlet and exhaust ports when sealing is desired. Valve springs require maximum fatigue strength and should not relax their spring tension despite high operating temperatures and millions of cycles of operation. For these reasons, Caterpillar keeps all processing, manufacturing, and inspection tightly controlled. The springs are made of extremely high-quality wire, and every inch used is inspected. An eddy current from a magnetic coil is run past the wire, and it detects any imperfections through the change in current characteristics. Any section of wire which has imperfections is automatically discarded. This is just another example of how details make the difference to Caterpillar. The valve insert seats which contact the valve face must be matched in hardness with the mating face. For this reason, they are usually manufactured from a high hardness material. As with other engine overhaul replacement parts, competition in valves, springs, guides, and valve seats is fierce. Imperial Cleveite, IPD, TRW, Eaton, and Federal Mogul, among others, sell these parts which will fit our engines. At first glance, they look like direct replacements. But close scrutiny, like the examinations done under Caterpillar's competitive test program, often reveal inadequacies not apparent to the naked eye. Consider valves and guides, for instance. If the thickness of the valve stem or bore of the valve guide are incorrect, one of two things could happen. Too much clearance might allow the valve to cock in a seat like this. Such a condition subjects the valve to high point loads and could fracture the valve. It doesn't take too much imagination to visualize the potential results of this type failure. Too little clearance prevents the formation of the essential film of oil. Without efficient lubrication, the valve will seize. Here is where the threaded guide has the advantage. With the threads to provide a path for a small controlled amount of lubricant, Caterpillar can provide the best of both worlds, close tolerances and proper lubrication. Remember, at Caterpillar, we take the extra steps necessary to provide a quality part. When you look at competitors' offerings, ask yourself some questions. Were the valves heat-treated properly and in all areas which require it? How good is the bond between the hard facing and the valve body itself? Do they match the valve material makeup to the particular engine configuration? Is the wire used for competitive valve springs of consistent quality with the proper tension? Do they check 100% of the valve spring wire as Caterpillar does? After you have considered quality questions such as these, look at the concept of component mismatch. Valves wear against valve guides, valve seats, and the rocker arms. If the hardnesses of these parts vary, one component will wear at an accelerated rate and fail early. By insisting on genuine Caterpillar replacement parts, customers greatly reduce the likelihood of mismatch taking place in their engine and take full advantage of the details that make the difference.